All right, guys, hope you've enjoyed the event so far. Got a lot of other great presentations, panels throughout the weekend, other features that are going to take place later after, not just this evening. It's going to be all throughout the weekend. We've got some great sky watches. Mark's going to be out there. We've got Ben, who has just presented in room B. Melinda Leslie is supposed to be out. We're going to be doing some great meditative work, C5, heist. If you guys are familiar, let's talk about that. If not, let's see how we can incorporate that into the discussion and see how we can expand our mind to the possibilities of how people are getting involved in this work and what they're doing to make sense of all of these things, to elicit responses, to engage and interact with phenomena, intelligences. And this is something I think is really important for us to hear from the scientific perspective, from the astronomy perspective. Mark has been involved with astronomy and has been an astronomer for years. He's looked at this in many ways and has been a photo analyst, has been looking into how we can make sense of what people are reporting, they're submitting, the material that people are curious about gets sent to those who can use the technology and to have the resources to actually try to figure out what we're dealing with. And Mark's been involved with MUFON. There's a lot of other really interesting work with special effects and things to show that there's just a lot of ways to get some of this material out there to the general public. He's been featured on a number of shows. You've probably seen him on some different networks and things that help to reach different audiences all across. So one of the things before I have him come up, it's really important that you guys know that this isn't just something that you can see today and then think of for till next year, but he's got a really awesome sky tour whole operation that you can tune into. He's going to be using this as a way to help encourage this a little bit more frequently than just once a year type of event, but we can actually see what's going on, viewing the stars on a more regular basis to try to find out what's going on, what we can learn from just viewing the beautiful heavens above us. So I'd like to bring up to the stage Marc D'antonio. Let's give him a hand. To be able to have him here is a really important part about bringing in the scientific arena, as well as we have people from, like you just saw, Nick Pope, from the government. We have people in the civilian sector, and research and the data points involved in all this is really going to be something that's a fascinating part of the discussion. So without any further ado, Marc D'antonio.
Thank you, Roy. I appreciate you coming. How many people have actually seen me talk before? Okay, so you probably expect me to go out into the audience and do stuff because many times I don't use podiums, by the way. You know where the podium comes from? When emperors had to deliver bad news, they hid behind the crossed shields of soldiers, and they delivered it from behind the shields. So this was a shield. Well, I don't have to hide from you. Yet. Hope I don't. But no, when I decided to become an astronomer, I realized that, and I was 9 years old, by the way, okay? This is my friend Darlene down here with her parents, Donovan and Alicia. Okay, I know. Okay, and Darlene was 9 when she bought my book. She's still 9 years old. She's still 9 years old. I was her age when I decided to become an astronomer. All right, and I never wavered. I probably should have, because I wanted to, if I wanted to make money, you don't want to be an astronomer. But the lure of the universe was really very impactful on me. And I felt that it was the most important thing to study because I knew that we were going to be out there someday. Now, when I was 9, we had only just landed on the moon. Yes, I'm that old. Okay, and yes, we did go to the moon. There are people that think we didn't. So, this talk is about my conviction that not only are they here, but there is a way they can get here that our current physics can actually see. And that's kind of important. Because right now, it's science fiction. It's Star Trek. It's coming. Ahead, we're back to none. I said, and off we go, right? The bottom line is that process, the thought process, is not so unbelievable. And we'll talk about it. And to do that, let's just begin with some early astronomy. In the early days of the ancient Babylonians, okay, they chronicled the stars. And they pecked out on stone tablets their observations of constellations and star patterns. Why? Because those were over their head. They could see them. They had no idea what they were. There were no ancient Babylonians that said, yes, there's stellar nucleosynthesis going on here, and we're converting hydrogen atoms into helium atoms. None of that. We didn't know. They didn't know. But over time, okay, there were other clues as to what was going on in the ancient mines. There were cave paintings thousands of years ago that illustrated these interesting anomalies in the sky that were recorded. Okay? And then 3,000 years ago in Mesopotamia, stone tablets were pecked out that indicated all kinds of interesting, notable objects in the night sky. And it took time, but then 1000 BC, we actually had the Babylonian tablets which showed up. The ancient Babylonians were actually pretty smart, okay? But they paled in comparison to the ancient Greeks. The ancient Greeks made, well, this here is what's called an astrolabe. It's actually an early metal instrument to measure the stars, to measure the sky. Interesting that they did that, right? Now, what's this have to do with aliens being here? If you think about it, an ancient civilization will first notice the night sky. And then curiosity, which, by the way, is a characteristic of every single living creature on Earth. Curiosity. It's imbued within you. It's built in. It's part of the DNA of the human species and the animal kingdom. Very interesting concept, curiosity. It drives us to do interesting things, you know? So, when we talk about that, curiosity drove the Chinese to observe their sky as well. And in 1054 AD, they saw a new star in the sky during the day. Something so bright that they saw it in the day. And it turned out, with our modern telescopes, to be this object. This is a supernova, a star that exploded and spread its gas out into the universe. That gas is made of the elements in our periodic table, which themselves were forged in the heart of that star. And this particular event played out trillions upon trillions upon trillions of times in the universe, and actually populated our periodic table, the elements, which makes up everything that you are. Every atom within you was made in the heart of a star. Kind of freaky, isn't it? You were all forged at hundreds of millions of degrees. Well, you just let that sink in. You think, wow, that's actually pretty cool. Any pizza left? But if it makes you think about it for a moment, I win. I mean, that's all good, right? So these supernova remnants see the universe with all kinds of things. This one was seen in the 1700s by William Herschel with his 43-inch telescope. Now, curiosity drove him to make a mirror that he could look in his telescope and see the image of stuff that the mirror could see. The mirror was made of a particular metal called speculum. It was a shiny metal. And every time, before he could observe with it, he'd have to go polish that mirror. Because during the day, it would end up fogging up and getting dull. And polish it. They didn't have ways to make glass in special curvature to actually illuminize the surface to make it a shiny mirror. They didn't have that capability, right? This is it. So he had to use metal. But Herschel did it. And William Herschel discovered hundreds and hundreds and hundreds of objects that to this day we look at and say, wow, look what Herschel discovered. Very, very interesting. Now, jump ahead a bunch of years to a 24-inch diameter telescope. Herschel's was 43 inches in diameter. And this one is 24 inches in diameter. A little bit smaller, but a different kind. This is a refractor telescope. It uses a lens system. Light comes in the end, it goes all the way down the tube, and get progressively smaller and smaller and smaller until it reaches a point outside of an eyepiece where you can see it. I worked in a telescope like this. It looked very much like this one, actually. And it was 20 inches in diameter. It was so big, the entire floor moved up and down to meet the telescope. When you actually moved, you were on a giant elevator all night long. And you just go to look at something, and now the eyepiece is 10 feet over your head, so now you raise the floor to get up to it. Sounds fun, except many times it was about 12 degrees in the dome. Fahrenheit, cold. Okay, so you can't heat a dome because it has a slit in it, and that warm air goes right out the dome. Even your body warmth can disrupt a very sensitive image. So what you did is you bundled up in clothes that would not allow the heat out. And what's that do? It makes you sweat even more. So it was really uncomfortable working in observatories in the middle of winter. But still, that's what you had to do to advance the science. Now, next we had a 200-inch telescope at Mount Palomar. Okay, the telescope itself is this tube thing sticking straight up towards you. And in the early days, the person that's doing the observing rode around in the telescope, inside that little tube at the top. So if the telescope was moving around, he went with it. Okay? And that's what happened back then. So we're advancing, but then eventually we ended up doing it a lot more smartly. Instead of riding around with a telescope, we actually created a robotic system, a system you could run from a distance, kind of like I did with our telescope. I'll tell you about it. This is the 32.8 foot diameter Keck, K-E-C-K, diameter telescope. It's a huge pair of telescopes that work in unison or separately. This is on Mauna Kea in Hawaii. Everyone wants to go there. It's cool. I want to go see it. Well, when it's 75 on the ground, you go up to the top of the mountain, and the temperature is below zero. Because you're going up 13,000 feet in the air. And by the way, your first visit, you'll need an oxygen tank to walk around with. Because otherwise you'll get dizzy and pass out. I haven't been up there. Okay, so it hasn't happened to me. I'll get there eventually. I'm looking forward to it. But, so we eventually learned how to do this better, bigger, and this is what we're doing here. Now eventually, we took to space, and we ended up with the Spitzer Space Telescope. Spitzer was fantastic. Spitzer was a little tiny mirror, 2.8 feet in diameter, just under 3 feet. And what did it do? It looked in the infrared. You know, heat. It only looked for heat signatures. Okay? And what did that mean? It meant that it could see things in the infrared that we couldn't see with our eyes, because our eyes only see in the visible range. Infrared's way out here. Okay? James Webb looks way out here. Even further, way, way beyond what we see. Right? And we'll get to that. However, this is what the Spitzer shows in the infrared arena. Now, infrared energy is all at the far end of the red part of the spectrum. So everything there is going to be a variation of red, isn't it? However, things were colorized by NASA and by JPL and by other universities that did the work to show these objects in a way that was more pleasant for the eye and more discernible as something interesting. Okay, so that's why they look like this. These are all false color and not the real color. Okay. Then we took to the Hubble Space Telescope, and Hubble showed us amazing things. That up there on the left, that's the Hubble image called Pillars of Creation. Who remembers that? Yeah, I see hands. The Pillars of Creation was a very interesting object. It's in something called Measure 16, the Eagle Nebula. We imaged it with our telescope. It's this big, it's tiny in our images. But the Hubble Space Telescope could see some tremendous detail, as you can see. Not only that, the Hubble Space Telescope also has an infrared imager. And on the right is the infrared image of this particular region. You'll notice that it looks very different from the visible light region that you see on the left. And that's because infrared can show you certain details. But the infrared Hubble has isn't good enough to show you all the crazy detail that the James Webb can show you. So this is the James Webb's view of that same region. Talk about pillars of creation, it's like pillars of holy cow. Right? Incredible. Yeah, and that's not even the end. There's even more of that. It's interesting. But then, we started to think, we wanted to look for other worlds too. So the Kepler Space Telescope, well before James Webb, was launched and found over 5,000 planets around other stars. Finally, we're reaching out looking for other worlds like our own. Ostensibly, when you look at NASA, every single mission to Mars and the outer planets was to look for signs of past or present life. Those were always experiments on board that showed that. This is cool stuff, right? Now, Hubble looked for what are called transits. When a planet passed in front of its star, as viewed from Earth, some of the light from the star would be diminished just a little bit. And this telescope was capable, that's not me expert, this telescope was capable of seeing those dips in the light, right? And it found a bunch of planets, tons of them. Again, up to 5,000. And then follow-on to the Kepler mission allowed us to find even more planets, right? Now that was called K2. It was a modification to the original Kepler space telescope. So it really means that we are finding all these habitable zone worlds. The habitable zone is that place around a star, and most of you know this, that not too hot, not too cold region where you can have liquid water on the surface. That's important. We came from that. We came from the sea. That's why you have salinity in your skin. It's a holdover of a vestigial remain of your time in the ocean. That's exactly what that is. Now, next came the TESS Space Telescope. This was a transiting exoplanet survey satellite. And this one had an interesting view. It showed, instead of Kepler, which was a laser pinpoint looking at one star at a time, this one was 24 degrees by 96 degrees in size all at once. The promise was that we would find thousands upon thousands of exoplanets all at once. And it fairly well succeeded on some of those goals. It was really cool. Now, James Webb, of course, comes along, and that is looking at light far out in the infrared. If the visible spectrum is represented by what you can see with your eyes, it's the width of the podium, then the infrared spectrum that James Webb is looking at is far beyond into the other room. And from the very end of the podium, all the way out to the other end of the other room. Okay? That's how big of a view into the infrared that James Webb could see. And this is the first image, and it looked at, it showed us light that we could never really hope to see. Because in the case of, on the left there, this is the Wide Infrared Survey Explorer, and that's the 1.5 foot diameter mirror. Look at the resolution. And then you have Spitzer next to the right, 2.8 feet in diameter. And then to the right of that, James Webb, 21 feet in diameter. Hubble's only 8 feet in diameter. So this is 100 times more capable. So we have a lot of promise for finding other worlds out there. We've also found worlds that have lots and lots of water and oxygen. Hey, that's pretty good. We breathe oxygen, right? So you may think, hey, we're good, we're doing better. Now, remember Hubble, Pillars of Creation, right? And you remember James Webb Space Telescope showing us this, right? Well, the other thing that we want to talk about beyond that, okay, and the reason I just showed you those last two pictures is because the difference in technology is 1,000-fold. You see so many more, so much better, so much higher resolution imagery. Now, you ask the question, well, is the U.S. government trying to make alien disclosure more palatable for all of you? I mean, we look at different movies and things, and we say, well, what role do movies play? Remember this one? What's the name? Yell it out. Yeah. And what was the name of the robot? Klaatu. Or was it Gork? It was Gork, wasn't it? Yeah, it was Gork. He knows. Okay. Klaatu Nicaragua. Right? That's what he said. The Gork. He said Klaatu Nicaragua.
That was, I think, his greed or something like that.
I think he told him to. Yeah. Cool stuff. Well, anyway, we're getting to the good stuff here. Right? If we look, okay, at movies, right, they portray aliens in variety of ways. Okay? The day the Earth was still benevolent aliens come to the Earth and warn us that if we're not careful, we can destroy ourselves. That was the previous one. And then we had an alien, xenomorph. We just come to eat your brains. Okay? So it was truly a horror movie in space, right? Then we had, of course, this one. What was this one? Prometheus, yes. And this guy in the white, these guys stood around 9 feet tall, and they were supposedly the engineers who created the human race, which they deemed a failure. And they were going to wipe us out and just start again. And we weren't going to have it. So that's what the movie was about. And of course, E.T. Phone home. Remember? E.T. was a great movie. It was fun. And it, again, benevolence, kind aliens coming here, we protect them because they need us, that kind of thing. And then, of course, Independence Day, where they come here to just destroy us. Why? I don't know. That one was never really made clear. Okay? But we also had Close Encounters with the Third Kind. Okay? I worked for years with Douglas Trump, who did the special effects for that movie in 2001: A Space Odyssey. A great man. And that, we saw all behind the scenes. it was interesting to see how Spielberg wanted to stick to what people in the UFO community were reporting. Didn't want to deviate too far, and he actually kept to some really cool reality in that particular portrayal of the movie. Okay, and of course, you know this guy. Who's that? J. Allen Hynek. He had a cameo in Close Encounters of the Third Kind. I thought that was pretty cool. So why am I showing you? I'm showing you that because we portray aliens differently depending on our movies and our media that we create. But you also have to say, well, would they even come here? Why would they come here? How would they see us? There's upwards of 150 billion stars in our galaxy. And we now know that there's more planets than stars in our galaxy. Did you know that? More planets than stars. So clearly, we don't stick out. They notice us. Stephen Hawking said we have to keep our heads down. Let's not expose ourselves to aliens. We don't want to expose ourselves before we're capable of dealing with them. That's what he said. Too late. I'll explain why. Okay? When you ask why Earth is so visible to alien life, it comes down to one thing. That's our pale blue dot, as Carl Sagan said. Blue dot. Okay? Carl Sagan was my favorite astronomer. Part of the reason I became an astronomer. Okay? The reason that Earth is so visible is because of this. Oxygen. We all need it. We all breathe it. Why? Because we're carbon-based beings. Carbon is the fourth most abundant element in the universe. You know what the third most abundant is? Oxygen. Second is helium versus hydrogen. Oxygen is something that our planet produced in copious amounts, and it was actually done rather quickly. You know, it's something that's called the Great Oxidation Event, and it happened 2.5 billion years ago or so. The G means giga, billions of years. And so 2.5 billion years ago, oxygen was formed in our solar system, in our Earth rather, and started building up. Now, any carbon-based life forms in our nearby solar neighborhood, any, are going to look at that oxygen buildup in our atmosphere. Because if they're carbon-based, they're going to need oxygen too, because that's the energy-producing, energy-catalyzing, energy reduction mechanism for carbon-based life. Oxygen. So if that's the case, they're going to look for oxygen. And we started standing out like a sore thumb over 2 billion years ago. So Stephen Hawking wanted us to hide, and our Earth had other ideas. And it showcased our oxygen to the whole universe in every direction. If you looked in our direction, you'd see oxygen in our atmosphere. How do I know? Because we're looking for oxygen in atmospheres. We're only 5,000 years into our written history if you go back to ancient Sumeria and the cuneiform tablet language. Okay? So after 5,000 years, we're looking for oxygen around other planets, around other stars. And if we can find that oxygen, well then guess what? We're going to say, we want to go there. There might be life there like us. Or life not like us, but life. And so we'll stand out like a sore thumb. And that's the reason why alien beings would have looked for our planet and found it long ago. They might have found it 100 million years ago. There was copious oxygen in our atmosphere. Right? They might have come 100 million years ago. Maybe 1 billion years ago. Well, heck, they have over 1.5 billion years already at that point to see oxygen building up here. So why couldn't they have come? Are we, at 4.5 billion years old, are we a life form that reached intelligence because it took this long in the 13.8 billion year history of the universe to get to this intelligence level? I don't think so. If you consider that we're pretty darn lucky to be here, considering we've had 5 major extinction events on our planet. We were reduced to almost nothing 5 times. The worst being 252 million years ago during the Permian period, when 96% of all life on this entire world was extinguished by a major volcanic eruption in what's now Siberia. The ocean temperature raised 21 degrees, killing off oxygen-bearing capability to the point where all the plankton died, further killing off oxygen production. We barely survived. And there there was one set of creatures at that point that really did well with them. And those creatures were dinosaurs. So because of that extinction event 252 million years ago, the age of the dinosaurs began. And because of another extinction event 65 million years ago, called the Cretaceous Paleogene boundary, and it's known as other names, the day the dinosaurs died, okay, the big Chicxulub impactor. Because of that, dinosaurs died. And those little creatures hiding in the shadows that would become us could rise to dominance again, just like they were in the Permian period before that major eruption. That's something you didn't know. Creatures that would become mammals 252 million years ago were dominant, but they were killed off. So in other words, does it take 4.5 billion years for intelligent life to come to fruition? No. It just takes that long when you've had 5 major extinction events to finally reach that point where you're now dominant. But it didn't necessarily have to be that way. What if we had no major extinction events? Maybe 252 million years ago, the little tiny vole-like creatures that were reaching toward mammalhood at that point would have succeeded. And maybe intelligence here would have developed, I don't know, 100 million years ago. So we'd be 100 million years into intellect and intelligence. We would certainly have done away with any medical issues. We certainly would have been spacefaring by this point. So because of that, other alien races elsewhere probably have done this. And we've got a lot to choose from, let's be clear. I mean, there's 150 billion stars minimum in our galaxy, with more stars than planets, and 20% of those are habitable worlds like ours, based on our best guess. And oh, by the way, there's about 2 trillion other galaxies with the same expectations. And we're not a big galaxy, by the way. We're kind of an okay size, we're not the biggest. The one that's heading right for us, the Andromeda Galaxy, has 1 trillion stars in it. 250 million? 1 trillion stars. They're going to come through, collide with us, go through us, change us forever to something different. And we'll never notice, even if we're here at that point. It'll just be a very slow motion thing. We're not going to change anything. We're not going to suddenly die. We're not going to. But there's galaxies out there with many more stars than the Andromeda Galaxy, and many fewer stars than ours. And so there's a whole bunch of these out there. And so at some point, those galaxies are going to have potential life forms. And they may have already happened hundreds of millions of years ago, billions of years ago. So it depends on what was afforded them, the opportunities that were afforded. Through all the 5 issues we had here, the 5 major extinction events, we prevailed. Isn't that great? I think it's a cool thing. So oxygen is very important, So the James Webb Telescope is going to be looking for oxygen. Go figure, right? We're doing it. And it's going to find it indirectly because it's going to use a technique where when oxygen atoms collide in an atmosphere, you can't tell that oxygen atoms are there directly. But it can tell when oxygen atoms collide because they give off a signal that's in the infrared. Based on how many of those signals it sees, it can infer how much oxygen is in an atmosphere. And if we can do that with 5,000 years of history keeping as an infantile species in the universe, then I think a civilization 1,000 years ahead of us even could do it with panache and do it very well. Don't you think? I know you do. You're sitting here going, when's lunch? So now we ask, if that's all true, what types of techniques and technology could an ancient civilization, or an ancient civilization to us, okay, that's been around the galaxy for 100 million years, leverage in order to come here? Well, there's a few. We hear about the warp drive, warp drive concept. In 1994, Miguel Alcubierre came up with an idea, hey, here's an interesting thought. If we get enough energy, we can build a warp bubble around our ship and literally pull the universe past us as fast as we can possibly do so, and go places very fast. We can actually reach Alpha Centauri, not in the 10 or 12,000 years it might take us normally at the fastest possible speed we can go, maybe in 5 days. 5 days, that's so cool. I could pack a cooler, you know, that'd be all I need if I turned around and came back right away. So I need 10 days of food, I can do that. All right, well, let's see how quick your area. The trouble was, it required a stupendously colossal amount of energy in order to make that warp bubble. So it wasn't going to happen. So it became a thought problem, a fun thought problem. So it's not going to be that quick. However, there's more that we can do, all right? And for those that have ever taken a quantum mechanics class, this is not one of them, okay? But I have to share with you something to do with the 4 fundamental forces that we know in quantum mechanics, because what this does, and you're not going to be bored by this, I promise, because I'm going to actually dance. No, that's a lie. I just lied, I'm sorry. But these 4 fundamental forces are critical. Now, the weak force is the reason you're here, because the weak force is how those elements I told you that are formed in supernovae can change into other elements. It's how you can get a carbon atom turned into a nitrogen atom and then possibly an oxygen atom, okay? It's called beta decay. You don't even have to worry about that. All I'm telling you is it's important to why you're here. The strong force is what basically holds all those atoms together, all right? The electromagnetic force is light, the reason you can see us, see each other, okay? Now, gravitation, on the other hand, that one, that's the mysterious force that we don't really have a good answer for. All of these forces we can describe as a wave and a particle. We can write a wave, theory, like a wave, right, like an ocean wave, right? But we can describe those mathematically for a weak, strong electromagnetic force. Light is what's called a dual particle nature, right? It can be a wave, light wave, or it could be a photon, right? Well, we've discovered in gravity that gravity can be a gravity wave, right? Ooh, that's new. Einstein said we never find those. Well, we did. Well, the one thing that's elusive that we haven't found is the graviton, the analog to the photon. But what if the graviton is something that's just being elusive because we can't really leverage the technology to capture it yet, which I think is what it is. So if we look at leveraging technology, we have to think about something called string theory. Now, basically, string theory, again, if you think about it, we're talking about protons. Like in a hydrogen atom, you have a proton, you have an electron, and you imagine an electron going around the proton. That's your model of the atom that we think about. Well, what if we look at the fact that those protons are actually vibrating, and that the electrons are actually moving so fast that they're everywhere at once? I know that sounds crazy. Believe it or not, that's what quantum mechanics wants you to think about anyway. It's really whacked out. I'm not kidding. So, yes out there. Yeah. So, but if you think about the proton as energy of vibration, and you consider that this end is where the particle is, and that end is where the particle is, what's in between? What's in between is the energy, the path that it took. Aha, we'll call that a string. Now, trust me, you're not going to have to worry about this beyond this, okay? But the point is, we talk about how particles are actually strings. And in string theory, if you go down that path, then our world is actually 4 dimensions, X, Y, and Z moving through time. 4 dimensions. Everything you experience, everything you've done is in this 4 dimensions. Everything. We've never done anything outside of that. However, if we look at a variation of string theory called Mandel-Sundrum 1, again, don't even memorize the name, who cares? That was actually perfectly timed. Now we go dramatic, What it means to us is that we can now look at our X, Y, and Z moving through time, and then we can consider a 5th dimension called the bulk. So outside of our 4 dimensions, we have another. Stay with me on this, okay? And there's something about the bulk that we'll talk about shortly. and then past that is something called the Planck membrane. All right? Now, don't worry, I'm going to explain all this. But the clues to how this is working with a UFO can be found by looking at their shape. What shape are UFOs? They're circular or triangular now, right? Why are they circular? Any ideas? You can talk to me, I don't have any problem. Yell it out there. Yeah, Darlene. Does he blow it up? Did she say sea circles? Okay. Interesting concept. See, children have the coolest observations. Thank you. Roll your eyes. That was a good observation. So really what it comes down to is if you look at the circular shape of a UFO, you have to think about how they would actually travel interdimensionally, which I'm not expecting anybody to do. But aren't they possibly particle accelerators? Did you notice that all of our particle accelerators are round, right? The outside ring in a particle accelerator can actually dispense the particles. The inside ring can actually be a protected area inside, all right? We hear about these ships only being 30 feet in diameter. This is a small particle accelerator, right? What shape? Circular. Well, if we could figure out the technology to shrink that down to be very efficient at 30 feet in diameter, then you can have a ship that could actually generate certain particles that will help you get outside into that fifth dimension I was just talking about. And why does that even matter? I'll show you. Now, one of the problems that when you accelerate particles in a circle, like accelerators do, you're forcing them to go around in a circle with a magnetic field. When you do that, they don't like that, and they give off synchrotron radiation, which is not good. That'll kill you. So I'm sure they figured out how to deal with that. That is something you'd have to figure out. All right? But this is why it matters. If you have a particle accelerator, you can generate certain particles that I keep saying is certain particles, not telling you anything more yet, that live out in that fifth dimension. And those particles actually have a name. They're called Kaluza-Klein particles. Now, here's the interesting thing. If you look up Kaluza-Klein and CERN, C-E-R-N, you'll get a beautiful paper written about them. Why? Because CERN is investigating them. Why? Because they have really cool characteristics. Wow, neato. How do you generate them? Well, right now we have to generate them by using these very powerful particle accelerators. Well, what's another way to generate them on a constant basis? We can use fusion, a fusion reactor. These particles are, in certain cases, 10 to the 16th times more powerful than the gravitons holding you to your chair. So in other words, they're extremely powerful particles, right? So, and when I call them particles, we do mean gravitons. They are gravitational particles, bundles of gravity. Now what's interesting about them is that at that power, that complete intensity, they also generate something called micro black holes. Now wait a minute, where are you going with this? Micro black holes are very interesting because these will create visual effects. So if you saw a UFO in the sky, what might a micro black hole sheath around a UFO object, and I'll tell you how it matters in a bit, but what might a micro black hole sheath around a UFO mean for what you're seeing with your eyes in our four dimensions? It would change colors, it would shimmer, it might pop out, pop in. It might seem to disappear from one spot in the sky and appear over here. These are all observations that are made by people who report UFOs. So, as Avi Loeb, I know, and we've done shows together, as Avi Loeb would say, we can't ignore the possibility that we're looking at Kaluza-Klein particles that are in play, because they would cause those visual effects. But wait, why? What does that do for us? What do these particles do? Well, these particles, I think, are the secret to how a UFO and an extraterrestrial civilization of sufficiently advanced nature can reach us and get here. Now, the way it works is that these Kaluza-Klein gravitons are generated by a fusion reactor in a UFO, which is a circular object. Okay? They sheet the ship with these collusion-flying gravitons. The gravitons themselves create micro black holes in a certain proportion. Those last a few nanoseconds. Those are billions of a second. What good are they? Singly, they don't do that much, but as a group, if you keep a constant flow of them going, by using, by the way, a fusion reactor, then you could generate enough of these to actually begin to tug your ship into that fifth dimension, because that's where these KK particles actually come from. And so your ship will get dragged into this bulk space, this highly warped space in the fifth dimension. And what does that do? Well, first of all, these micro black holes also don't allow our own gravity to get to them, because they absorb the Earth gravitons too, as well as some light causing the video, audio, and possibly audio effects that we see. Okay, so that means that the ship itself won't be subject to our gravity. It'll tend to look like it's floating kind of like a leaf. Another observation we hear all the time about UFOs. It look like it's uncontrolled, fluttering like a leaf. Okay, that's a very interesting finding. Now, the gravitons themselves, they pull the ship into the bulk. And what's the bulk? It is a highly warped space. Okay, and the farther in you go, the more warped it is. But what does that do for us? The warp inside the bulk is what you would see if you were in the ship. What does it do for you? Inside the bulk, when your ship goes into the bulk, the farther in you go, the distant stars start getting closer. It shortens all the distances in the universe to you from your perspective. It's a warp effect. It's a real warp effect. This isn't just me saying this. This is other physicists and people in the aeronautical engineering field are saying this all the time. And so what that means is you can actually punch out of our four dimensions by creating a bunch of these particles on your ship with a fusion reactor, sheet your ship with these particles. Those particles belong in that warp space. They pull your ship into the warp space. The more you generate, the farther in you go. The more warped it is, the closer distant objects appear. And if you are close to, say, the Planck membrane, that far distant membrane, then you could actually reappear close to a distant star in a heartbeat. That means you could go to Alpha Centauri in as little as 20 minutes by some calculations that have been done. Isn't that crazy? We went from 12,000 years to 5 days to a few minutes. Wow. I can see tourist trips to Pluto. We're going to leave for Pluto at 3:30. You'll be home in time for dinner. You go out at 3:30, you get the ship, you punch out, you generate collusion-flying gravitons around your ship, you disappear, you punch out, and you punch in over Pluto's entry point where that location is, and you're there for an hour. Oh, look, Mom, it's Pluto. Yes, son, those are all nitrogen, those are nitrogen mountains down there, and H2O is bubbling up and causing what look like those giant things in the middle of Sputnik, Planitia. Oh, that's so cool. Can we do it again? Yeah, we'll bring you sister next week. Right? I know that sounds crazy, it sounds foolish, but think about it. That's our future. Field trips to the sky, field trips to the solar system. We're going to go see Jupiter's moon Europa today. It's a 9-minute ride to get there with this particular system. 9 minutes, but we're going to take it easy. We're going to go easy. We're going to go, because we're going to give you lessons along the way. You need time to learn what you're going to see. So we'll have a specialist, an astronomy specialist by the name of Marc D'antonio, who's going to give you all the information about Europa before you arrive, so we can go down to the surface and kind of look and see what's going on. But don't worry, you won't have to worry about the fact that Europa doesn't have much of an atmosphere. Why? Because we're going to be phasing in and out. What? We're going to be going in and out of the bulb so fast that we won't be subject to either one of those locations' limits. So we'll be able to be there and not be there, but you'll be able to see it all. It's how USOs operate in our oceans, I believe. Some of you know the story. Who's heard the story about the USO that I've told? Okay, Cheryl has. You did. Well, I just did. Earlier, I did. Yes, that's right. I was surprised. I don't remember telling you. They did. Sorry. Yeah, well, anyway, I was on board a US submarine as a guest, doing Navy work, and I was seasick. I'm not too proud. I was totally seasick. When the sun's on the surface, it rolls and rocks like you can't believe. So I was like, whoa, this is no good. I know there's no windows. Okay, so I hung out at the periscope where I could at least see something. That didn't work. So I got a medicine that they gave me in a patch called scopolamine, which wasn't available for the public at that point. The Navy was testing it. That's where it came from. So it's kind of cool. So I was a guinea pig, I guess. Well, anyway, that patch helped a little bit, but made me a little tired. It kind of worked like Dramamine, but not quite. A little better, much better results. Well, anyway, I was sitting in the sonar shack next to a guy who was running the sonar, and he proceeded to yell out as I was just drifting off to sleep to get my stomach back. Con sonar, fast mover, fast mover. And I bolted away going, what? Fast mover, was that a torpedo? Are we going to die out here? Why did I say go on this trip? It was an option. I should have said no. And then the executive officer comes around, nonchalant. Now you got this torpedo coming in the ship. He comes around. He goes, what do you got? Well, a little more excitement, please. You know. And the kid says the bearing and range, which I didn't really hear, because it's noisy on a boat, way louder than you hear here. There's a lot of stuff going on. But then he said, okay, what's the speed? And the kid was incredulous. He'd never seen this before. He turned and he had both his hands out like this. Several hundred knots, sir, which is several hundred miles an hour. Underwater. Okay? Underwater. So you say, well, wait a minute. Nothing goes that fast underwater. Well, it could. If a ship is using collision-calling gravitons and it's going into the boat and out of the boat back into our dimension quickly, it can actually make discrete jumps all through the water, along, up and in, out and in, out and in, punch out, punch in, punch out, punch in, all along the way to make up a line path. And if it does that, the benefit to that is it won't feel the pressure of the water like that unfortunate Titan's submersible crew and visitors felt when the sub imploded. It would never happen. They wouldn't feel the pressure because they're not subject to it. They're half in, half out the whole time because they're fusion reactive to keep those particles going. Okay, so if that's the case, that'd be pretty cool. So I said to the XO, being Mr. Important Guy, and I saw right there, I was invited to him, important guy. You know where this is going. I said to the XO, I'm familiar with these fast movers. Is there anything I can help you with? He said, D'Antonio, right? I said, sir, yes, sir. He said, you have any good time spark? Sir, yes, sir. He said, let's keep it that way. And I walked away. So, bottom line was, I didn't get an answer until I did a job for the Joint Chiefs some years later. I'm a Navy model maker as well as everything else. I don't know why, but I am. It turned out I'm somewhat of a go-to guy for underwater technology, I guess. Go figure. There's always a place for science. Stay in science. And so I went to a job. I brought this project down to Washington. And I sat with the guy in charge of our U.S. Navy. The guy. And I said, well, in my head, I kept saying, don't ask it, don't ask it, don't ask it. The words already came out. What's the fast forward program? And I'm like, and I had this wince on my face, so I knew I shouldn't have asked that question. He kind of laughed. He goes, I'm sorry, Mark, I can't talk about that. I went, okay, that's okay, thanks. I walked away going, oh my gosh, it's real. It's real. These things are really out there. And it's the directive of the Navy to observe and report what they see. And that's it. When it comes to these guys, they can't do anything about them. They haven't made any offensive moves toward us. So therefore, we'll observe and report. And that's it. And that's what we do. It's what the Russians do. It's what the Chinese do. It's what other nations have done. They observe and report. So, how could they move? If they use this procedure right here, that's how they can move. Okay? So, travel time is shortened immensely, and they'll be seen in strange ways as they move in and out of this bulk area. And all the effects that we see of UFOs, like I said, changing color, shimmering, fading in and out, overtly vanishing, that's evidence, potential evidence, of these collision-climb graviton propulsion in play. I think that's pretty cool. And again, I'm not the only one. So the verdict to me is that these UFOs might be using very, very strong gravitational fields in order to move themselves through space. But they're doing it by punching out and punching in. They don't travel the intervening distance. If they want to travel the intervening distance, then they punch out, move a short distance and punch in. And maybe moving through water, for instance, that's a safer mode for them to travel. So you can see them. Maybe that's why we don't see them. Maybe that's why we haven't found them. Because they don't show up in our regular viewable dimensions. But they show up on sonar for some reason. Because every time they punch in, they leave a trace that goes to the sonar operator. Maybe that's how it works. I wish I knew the answer. So you ask where the aliens are hiding, and I've heard people say, "Oh, they're on the moon. Maybe they're on the far side of the moon." I heard that still to this day. But I'm sorry, but that doesn't work for me. I'll explain why in a sec. Maybe they're in a perpetually dark crater. Oh, on the south side of the moon, the South Pole, there's a crater called Cabeus, and we sent with a mission called LCROSS, LCROSS. We sent a rocket booster into Cabeus crater and had it collide. Why? To see if it would throw up any water vapor, or not water vapor, but ice, okay? And that ice would indicate that there is ice in the South Pole. The crater is in the shaded regions that are permanently in shadow. And thus we could put a base there and have plenty of water. That was the whole idea, look for water on the moon. Well, it turned out that, yes, there was plenty of water there, but also it turns out that there's plenty of water in all the rest of the soils of the moon. We just have to access it a little differently. So we do have water all over the moon. So yes, we can make a base almost anywhere we want on our moon. Okay? But what about inside the moon? Remember all these hollow moon theories? And what's the strongest argument you hear for people saying it's a hollow moon? Anybody? Yeah.
Rings like a bell if you hit it.
Rings like a bell, yeah. And what's a property of bells? What makes them ring? Why do they ring? And first of all, are bells, okay, yeah? What's he saying?
It's hollow, there's something inside to hit and make the sound.
Oh yeah, the ringer, right? Yeah, that's very true, right? But if you look at an actual bell, you can look up inside the bell, can't you? Right? These bells are open on the bottom, you said. They're open on the bottom. The moon's not open on the bottom. So how come it can ring? If you had a hollow sphere and you hit it with a hammer, it'll go tick. Bong. Ringing is a function of solidness. If it's solid, it'll ring. If it's not, it won't. If it's hollow, it won't. It only rings, okay, a ring is resonance of sound waves inside of a chamber, the open chamber of bell coming out of the open end. That's not what we got on the moon. This has been a misunderstood quote for decades. Okay? It rings like a bell. No, it doesn't. What's actually ringing? Well, seismic waves. When something strikes the moon like a meteorite, Apollo-era detectors detect seismic impact. Okay, and you'd see a vibration on these detectors go down, hit the other side of the moon, and bounce back, and come back to the detector. Look, it keeps going back and forth. Why is it going back and forth? Because the moon is nearly solid. And so it's very efficient for sound waves to travel through rock solid crust. And sound waves can only travel through air otherwise. So would the hollow moon be full of air? No, that doesn't make any sense. There's a park in Pennsylvania that I'm going to ask if anyone's ever been there. It's called Ringing Rocks State Park. Have any of you ever been there? Okay. If you go, they give you a hammer and say, please hit our rocks. And you hit these solid rocks that have almost the same composition all throughout. I'm that guy too. No, sorry. This is not a great guy. Okay? You don't have to worry. And so the thing is that these rocks, when you hit them, they ring. Okay? And they ring and they ring and they ring. It goes on and it doesn't stop. And it's precisely because it's solid that they ring. So the moon is not hollow. The moon is definitely solid. In fact, it's nearly solid. Right? So then, if you want to see about the moon and see why aliens would be hiding on the far side, well then all you have to do is Google this, the LRO quick map. If you do that, you can go down to seeing just a few feet per pixel on the moon and look over the entire moon and check it out. It's really cool. You'll lose time, you'll miss dinner. You're can probably miss breakfast and lunch the next day, because once you start looking, you can't stop. You can go see all the Apollo sites, you can see the tracks left by the astronauts, you can see the flags in some cases. Because this particular probe, the Lunar Reconnaissance Orbiter, LRO, was 30 miles above the moon, and it still is, circling the moon, mapping the moon. If you were on the far side trying to hide, sorry, you're not going to be able to hide. That's all mapped too on LRO. You can go check out the Lunar Reconnaissance Orbiter, quick map on the far side of the moon, and look right down at the same resolution and see all these amazing things. It's cool. So that is something that I think negates the option to say that the moon would be a good place to hide. We're all over the moon. We're not there, but we're all over the moon. Not a good place. Where else? Well, this is sort of a hint. I think that they go where we are not. And where we are not is in the deep ocean. Right? There's ample evidence of this. So here's an interesting, they don't need to read all this, but in 1957, the Kitsukawa Maru crew was traveling and they saw these objects leaving and entering the sea. And they gave a latitude and longitude for where this was happening. And when you look at that on Google Earth, you find out that it's right near the Marianas Trench, right off the deepest spot in our oceans. Now, I told you about these ships that are underwater, these potential UFOs traveling in the water at very high speeds, punching in, punching out, not really subject to the water. So they're going to go over and out. They're going to go into the Marianas Trench and sort of hide there, phasing in and out the whole time, which is easy to do if you've got a fusion reactor. Just keep the fusion reaction going. You go to sleep, wake up, okay, it's still going. And it's going to do itself. It's going to work itself. So that's going to help them stay out of our sight. They've perfected the technology, in other words, if they actually do it this way. Now, another thing, in 1963, there were these naval maneuvers off Puerto Rico, and there were a bunch of surface ships and a bunch of submarines, 5 submarines in total. And one of the submarines broke formation because there was an unknown object that they were tracking. They tracked it moving very deep in the water, then very shallow in the water, and then at very high speeds. Sound familiar? This was in 1963. And they tracked it for several days. And this is the start of us learning about the U.S. Navy's version of fast movers. And that's what happened there. And go figure, how are they doing it? They're doing it, I think, by doing that phasing in and out, going from our 4 dimensions to the 5th and back and forth. And doing it's basically, it's called an oscillation. They oscillate back and forth at very rapid amounts of speed and time, so they can actually do this. So when you ask where they're hiding, and you say they could be among us, who remembers this show? Yeah, what was it called?
People of Earth.
People of Earth, that's right. Remember who these guys were?
I don't remember their names.
Oh, okay. There's Jeff. There's Kurt. There's Don. Okay. Now, I laugh. This is sort of like the end. But what's funny is, we talk about all the technologies that could be in play. And we've done shows indicating that they've been here. And what's important about this is it shows the classic gray, the classic reptilian, and the classic Norwegian. Yeah, the Norwegian guys. Thank you, Nordic. Sorry, I did a whole talk, set of talks in Norway, and I don't remember. But it was the Nordic. Thank you. And so, interesting how science fiction brings all these things together, and all these thought processes to the forefront of our mind. So I think it's pretty interesting, and I think that it's a way in which we can, just thank Productions for helping us with this disclosure, because that's what we're seeing here. So when you wonder about where they're hiding, they could be right out there in the audience, and we may not know it, because there have been talks about that too. I had some very frightening experiences, which took me to surgeons to remove things that were implanted in me. And a week later, they vanished from the hospital. Now, that was something that I didn't expect. I'm a science guy. This doesn't happen to me until it did. Right? So, there are a lot of mysteries out there. This will remain one of them, as far as I know. In any case, I want to thank you for your attention. If you have any questions, I look forward to talking to you. One last thing I had to mention. One last thing I want to mention. Tomorrow night, I'll be doing the Sky Tour live stream. I think it's in this room. Is it in this room, Daniel?
It is.
Okay.
Tomorrow.
So we'll have up on the big screen, we're going to have our live observatory from Arizona. It might be cloudy and rainy here, but it's going to be perfectly clear in Arizona. Already checked. They ordered it. Okay. And we're going to be looking at a galaxy that's currently experiencing a supernova. One of its stars has exploded. And we're going to show you that here. We're going to show you other things in the universe. Because we bring you the universe live in real time. And so we're going to screen this to the world. There's going to be a lot of people watching from all over the world. And then we'll have you in the audience if you choose to come here. It's 9:30 tomorrow night. At 9 o'clock tonight, I'll be with Ben Hansen, and we're going to do a skywatch. Right? His skywatch depends on clear skies. Mine depends on a clear sky and a place that has 300 clear sky nights a year. So I have better odds. In any case, thank you guys.